So, we now have these really powerful rules at our disposal, right? We have all these differentiation techniques. We now know how to differentiate sums of functions, products of functions, the product rule, quotients of functions, the quotient rule, compositions of functions using the chain rule. The problem at this point is still the functions we're working with are fairly limited, right? We can only really differentiate powers of x, right? X to the n, or that gives us polynomials and stuff like that. But the functions we've been working with are fairly limited, so in comes the next couple of sections. First up, derivatives of exponential functions, right? So this should be a pretty big question to you. What if you want to differentiate an exponential function, right? Base a, so that's just some constant, a to the x. What's the derivative of this? Well, I'll just tell you, right? The fastest way to get through this is for me to just tell you the answer. It turns out it's natural log of a, so ln of the base times a to the x. And what you'll want to do is simply just commit this to memory, right? So if you ever have to differentiate a to the x ever again, which you will, derivative of a to the x is, well, it's almost the same function. It's a to the x, but times ln of a in the front. And therefore, right, this is interesting, therefore, what is the derivative of e to the x? Right, we have the special number e, 2.72 roughly. We've got the special number e that we use all over the place, right? It's the base of this natural log up here. But what is the derivative of this? Well, using this rule, here my a is e, so it's going to be ln of e times e to the x. But what is ln of e? Well, remember, anytime the argument of the log matches the base, that's just 1. So ln of e is always 1. So this is just e to the x. And this is really nice. So this special case, I'm going to write this separately and sort of box this off. The derivative of e to the x, so up here we had a to the x, any old base a. Now we're specifying our base is going to be e. The derivative of e to the x is just e to the x. That's really, really nice. Right? This function e to the x is its own derivative, right? The derivative is itself. And it turns out that this is why this number e is so special, because it's the only function, and the only function in all of mathematics that has this property. It has this property that when you differentiate it, it equals itself. Or another way of thinking of that is sort of you plug in a value into e to the x, right? You plug in a value, maybe 3, you output e cubed, right? So that's the value of the function, but that value is telling you more than just the value of the function. It's also the slope of the function, right? Because the derivative would also be e cubed. So really interesting function that the value is the slope. That means as the values get bigger, it gets steeper and steeper and steeper as the graph goes on. So this is actually why this number e is so important. It's because it's the function that has this property. It differentiates to itself. It tells you its slope. So with that, we'll do a few examples. Here's just a few basic ones. Let's differentiate 8 to the x. So what's the derivative of this? Well, here our base is 8, so the derivative should be ln of the base, ln of 8, times, I'll put brackets around it, I don't really need it here, but it looks a little prettier, I think, ln of 8 times 8 to the x. Great. B. F of x is going to be 3 times e to the x. Then what's our derivative? Well, anytime you have a constant times a function, the derivative is just going to be that constant times the derivative of the function. So it's going to be 3 times the derivative of e to the x, which is e to the x. Okay, like I said, just doing some simple ones here. We'll do one more. F of x is x squared times e to the x. Well, now this is a little bit more complicated, right? What do I have here? I should really think of this as a product of two different functions, right? I've got x squared times e to the x. So if I'm viewing this as a product, which is pretty much the only way you can think about this, if I want to differentiate it, I have to use the product rule, right? Product, so I differentiate using the product rule. So using the product rule, it's going to be the first function, x squared, times the derivative of the second function, derivative of e to the x, plus the derivative of the first function times the second function, e to the x. So again, we haven't done any calculus, we've just written down the form of the product rule. Now let's actually take these derivatives. We've got x squared times the derivative of e to the x, which is e to the x, plus derivative of x squared, 2x, times e to the x. And that answer is totally fine, but there's some factoring I can do here. I might as well factor. I've got x common to both of them, and I've got e to the x common to both of them, so we'll factor out x e to the x. And we're left with x from the first expression plus 2 from the second expression. Alright, so this is more exciting. Now we can work with other functions other than just these polynomials, these powers of x, right? Now we can throw in exponential functions and still go through and use the product and quotient rules accordingly. What I'd like to do is work with compositions as well. And that means we need the chain rule. So let's see, using the chain rule, we have the following. We have, let's say I want to differentiate compositions that look like the following. It'll be a to the, not x, but a to some function of x. Alright? So it's a to some function of x. And I ask you, what's the outside function here? Well, the outside is this exponentiating thing. It's a to the x. And then we've gone and plugged in f of x into that. Right? So using the chain rule, we differentiate the outside function first. So we get ln of a times a to the, and the inside function stays exactly the same, a to the f of x. Right, so differentiating this is just like differentiating a to the x, where I've got this inside function. But remember the second half of the chain rule says, okay, first half is you differentiate the outside function, leave the inside the same. Second half says now you differentiate the inside function. So times the derivative of the inside function, f prime of x. And this is the chain rule in action. I gave you the general chain rule. I also gave you the special case for functions that look like g of x raised to the power of n. I call that special case number 1. This is what I'll call special case number 2. Special case of the chain rule. And that is because we don't really need the general chain rule in this class. We're not going to work with that many functions. So as long as you know these special cases, how to apply them to functions that look like this, compositions that look like this, that suffices. And I will point out that, again, most often we don't have weird bases like a, right? Most often our base is just e. And the formula is much nicer if your base is e, because this guy is ln of e, that's just 1, that goes away, so you just have e to the f of x times f prime of x. Right, and what this is saying is if you want to differentiate a function that looks like e to the f of x, all you have to do is leave the function alone, leave it alone, but multiply it by the derivative of the exponent. So we'll do several examples of this right now. Alright, for example, let's say f of x is e to the minus x squared. What's our derivative going to be? Well, the chain rule just said, okay, if you want to differentiate, this is more complicated than just e to the x. It's e to a function of x, where our function is minus x squared. But as we just saw, chain rule says, okay, the derivative is going to be just the exact same function, e to the same function, times the derivative of that exponent, the derivative of minus x squared. So now I have to actually compute this derivative, right? But hopefully at this point you don't think derivatives of minus x squared are particularly difficult. It's just minus 2 times x to the 1. And as I've written it, this answer is correct, but you should clean this up a little bit. This will be minus 2x. Looks a lot better if you write the simpler stuff out front. Minus 2x times e to the minus x squared. And there's our derivative. Right, so if you want to differentiate e to a function of x, it's the exact same function, just times the derivative of the exponent. How about this one? Actually, probably need more space. B. Y is 4 times e to the 2x cubed plus 3. So notationally I could write y prime here, but if I have y, people tend to like going dy over dx. So again, just alternate notation, I'm just mixing it up a little bit. Derivative of y with respect to x is what? Well, it's 4 times a function, so it's going to be 4 times the derivative of that function. And what's the derivative of this function? Well, it's e to the 2x cubed plus 3. Right, it's e to a function of x, so the derivative is the same function, but now times the derivative of the exponent. And we'll just do this on the fly here in situ. Derivative of the exponent would be 2 times 3 is 6. X squared, right? Lower the power by 1, plus derivative of 3, which is 0. And if I clean this up, I've got 24 x squared e to the 2x cubed plus 3. There's my answer. All right, let's keep going with this. All I want to do now really is a bunch of examples. Let's see. I don't know if I was labeling them before, but we're up to our third example, C. Let's call it G. G of, how do we even change the variable? Call it G of t. This is going to be t plus 3 squared times e to the 4x. Okay. So we want to differentiate it. We want to find the derivative. So in come quite a few rules here, I think. Right? I've got, if I'm viewing this as a function, the best way to view this, I think, is as a product. Right? It's t plus 3 squared times e to the 4x. That's how I'm going to think about this. So as a product, the first thing I need to do to differentiate it is use the product rule. Right, so it's going to be, the derivative would be of the first function times the derivative of, oops, I went with an x here, my variable is t, times the derivative of e to the 4t. Again, that's why I have d over dt, because my variable is t. It says differentiate with respect to t. Plus the derivative of the first function, times the second function, e to the 4t. Put some brackets around that to make it clear. So now we have to evaluate these derivatives, right? As I always say, I haven't done any calculus yet. I've just written down by the product rule what the form of the derivative should be. So what do we have? We've got t plus 3 squared. Now we need to differentiate this. So this is e to a function of x, or a function of t in this case. So my derivative, using the chain rule, is going to be e to that same function, e to the 4t, times the derivative of the exponent. And we'll just do this on the fly because this derivative is not hard. Derivative of 4t is 4. Although sometimes these functions that you have up here, sometimes they're actually really complicated to differentiate, and maybe you want to sort of not do it on the fly, write down, okay, now I have times the derivative of that exponent, but in this case it's pretty simple. Plus, what about this? Well, this is one of these examples from last time, right? This is a function of t raised to the power of 2, so I'm really using the chain rule here, but it's a special case number 1, the derivative of this, so it's 2 times, the inside stays the same, t plus 3, and the power decreases by 1, but now the second half is now times the derivative of the inside. Derivative of t plus 3 with respect to t is just 1. So this is times 1, and then times e to the 4t. And we're done. There's the derivative, but I guess I'll clean this up a little bit. We've got t plus 3 common to both of them, so I'll pull out t plus 3. We've got e to the 4t common to both of them, so I'll pull that out. And we're left with times 4 times t plus 3 plus 2. This has been factored out, that's been factored out, and that's just a 1. And I'll keep going, just one more step, t plus 3 times e to the 4t times 4t plus 12 plus 2 is plus 14. Which means I could even pull out a factor of, another factor of 2 out of this, but I'll leave it alone. Alright, so just recapping, I originally started off with a product. Alright, so I wrote down my derivative using the product rule should take this form, but each of these individual derivatives that I have defined, these now then require the chain rule. Right? This is special case number 1 of the chain rule, this is special case number 2, e to a function of x. Alright, so just have a few more examples here. The best way to do, or the best way to get good at math is really to do it, right? To do it yourself. But still you need to see, I think, several examples of this stuff in action before it really starts to click. So we'll just keep going through several more examples here. F of x is going to be e to the x plus e to the minus x, all divided by x. So there's some manipulation I could do to this. I could write this as e to the x plus e to the minus x times x to the minus 1, and I could view it as a product if I wanted, and use the product rule. But I'm not going to bother. The way it's written right now is as a quotient. I'm going to use the quotient rule. Alright, so my derivative, using the quotient rule, low d high, so we've got the bottom function, x, times the derivative of the top, minus high d low, the top, e to the x plus e to the minus x, times the derivative of the bottom, derivative of x, all over low squared, over the bottom squared, x squared. Alright, so what do we have? We've got x times, well, this is a sum, so to differentiate sums, we can just differentiate each function individually. Derivative of e to the x is e to the x. What about this one? This is going to be plus, okay, e to the minus x. That's now e to a function of x, right? It's something more complicated than x. But it's going to be the same function, e to the minus x, times the derivative of the exponent, which is just times minus 1. Right, the derivative of minus x is minus 1. Minus e to the x plus e to the minus x times the derivative of x, just times 1, all over x squared. And yeah, to be totally frank, if you just plug this into MyMathLab at this point, unless it gives you other rules, it would take this. But we'll simplify it. We'll we'll simplify it. What do we have? I'm going to, let's see. I'm not sure what the best way to simplify this is, right? As I always say, simplification really is in the eye of the beholder. We'll just distribute everything out and see how it looks. Ex times e to the x minus x times e to the minus x minus e to the x plus e to the minus x all over x squared. And I suspect what people would do to claim that this is as simplified as you can go is you would group the e to the x's together and the e to the minus x's together. But this is just sort of a preference. So what do I have multiplying e to the x? So I've got x and I've got minus 1 e to the x. And what do I have multiplying my e to the minus x's? We've got minus x plus 1. So I'm going to write that the other way around, 1 minus x, just because it looks a little prettier to always have a positive term in front. Right, so the 1 from this guy and the minus x from this guy, all over x squared. Although I'm not sure the simplification really is a whole lot simpler than this expression we had down here. All the examples I've done so far, I was working with e because e is by far the most common base for the reasons I pointed out. It's a very nice number that results in the function having its own derivative. But for, I guess, completeness, let's do a few functions that don't have base e, or maybe just a single function. Minus 10 to the 3x squared minus 4. So what's our derivative? Well, for starters, the base here is 10, right? If the base was minus 10, I would have put brackets around the whole thing, but I don't have it there, so it's really just minus 1 times 10 to the 3x squared minus 4. So I'll write the minus 1 out front, right? So we're going to be differentiating 10 to the 3x squared minus 4. So what's that derivative? Well, if you look back at the special case, remember it's the same function. It's 10 to the 3x squared minus 4, right? Our base is 10 to a function, where the function is 3x squared minus 4. So it's the same function times the derivative of the exponent. So 3 times 2 is 6, x to the 1 minus 0. So really that behaves just like e to a function of x did. The one catch is I also have to multiply by the natural log of the base, right? So times ln of 10. That's why I left that space there, just to throw it in front because it looks a little prettier. And if I just clean this up a bit, that'll be minus 6 times ln of 10 times x. And I'm going to put a bracket around this because it's not clear that this is not ln of 10x. So now it's totally clear. Times 10 to the 3x squared minus 4. Alright, so this example, just for completeness, in practice where our base is pretty much always going to be e. So that's nice. A, B, C, D, E, F. Last one I'll do, let's say h of x is e to the x times the square root of 3x plus 2. So this is by far the hardest one we've done yet because I've made this function up here in the exponent much more tricky than the other examples. But again, just to get started, you look at the form and you say, okay, my function is e to a function of x. So my derivative is going to be e to that function of x, e to the x times the square root of 3x plus 2, and then times the derivative of the exponent. And here I'm not doing it all on the fly because the derivative of this exponent is actually going to take a bit of work, so I'm going to write down the whole thing times the derivative of the exponent. X times the square root of 3x plus 2. But this is sort of transforming the problem into these bite-sized pieces, right? First off, we want to differentiate this whole thing. Now I've reduced it to now I just need to differentiate the exponent. And you'll notice that exponent, if I want to take that derivative, well, it's a product. So to differentiate products, we use the product rule. And so this derivative should be the first function, x, times the derivative of the second function, square root of 3x plus 2. But I'll remind you here, remember, we never differentiate radicals, we always convert radicals to exponents. So here I'm going to write this as 3x plus 2 to the 1/2. So it's x times the derivative of the second function, plus the derivative of the first function times the second function. And once again, I haven't really differentiated anything. I've just transformed this problem of finding the derivative of this product into smaller bite-sized pieces. Now it's the derivative of 3x plus 2 to the 1/2 and the derivative of x that I need to find. So we've got e to the x times the square root of 3x plus 2 times x times, okay, so we differentiate this. We've got a function of x to a power. So differentiate the outside, the power comes out front, 1/2 times the inside stays the same, 3x plus 2, and the power lowers by 1, minus 1/2, plus derivative of x, which is just 1, times square root of 3x plus 2. And there's our derivative. I'll simplify this a bit, we'll clean this up, but there's the derivative. What do we have? We got e to the x to the square root of 3x plus 2 times, what do we have? Well, remember going way back to the beginning of this class, some of the review stuff with factoring, this is, how would I write this as 3x plus 2 to the 1/2. We've got something to a power, something, and the same thing to another power. What did I suggest when you're factoring? Factor out the smallest power that you see, right? So that would be minus 1/2 in this case. So I'll pull that out. That'll be 3x plus 2 to the minus 1/2, factored out. Okay, so times what am I left with? I've just got 1/2 of x, 1/2 x, plus, if I pulled out a minus 1/2 power from this guy, that leaves me with a whole power. So plus 3x plus 2. Right, check this if you don't believe me. 3x plus 2 to the power of 1 times 3x plus 2 to the minus 1/2 will indeed, when you add these exponents together, minus 1/2 plus 1 is positive 1/2. Okay, so now, again, this is just simplification. I'm just trying to make this look a little bit prettier. I'm going to write this stuff out front now. How many x's do we have? We've got 3 x's plus 1/2 x is 7/2 x. So that would be 7/2 x plus 2 over, this is the square root of 3x plus 2, and then all of that is multiplied by e to the x to the square root of 3x plus 2. And there's my final form. I claim that's as pretty as it can get. I think it certainly looks a little better than this expression. Although this one's completely correct, but this one looks nicer. It's easier to read. So this was by far the hardest one we've done yet because we had to differentiate this more complicated exponent. But like I said, if you understand these rules, you can sort of mechanically go through this process. If I have a product, to differentiate that, I need to use the product rule. If I have a quotient, to differentiate that, I use the quotient rule. If I'm working with these compositions, I apply the chain rule. And you just go mechanically down the road because each one sort of simplifies your problem to simpler derivatives where you reevaluate the process again. Maybe your simpler derivative turned a product into something where you have to use the chain rule. So yeah, we'll stop here. And the next section is going to be, now that we can differentiate exponential functions, now we want to throw logarithms into the mix. So we'll talk about differentiating logarithmic functions. Thanks.